Good afternoon. Welcome to course Thermodynamics of Materials. Today we are into lecture 101 and 102. So we actually kind of completed the topic, last topic, these four issues that make thermodynamics a difficult subject for the students. And this was actually this was the last example for the fourth issue. Fourth issue was concept. Fourth issue was concept of equilibrium, and this was the third example. See, third example, and this is about iron carbon oxygen diagram and carbothermic reduction of FeO. This we discussed. But one point we missed that I want to fill in today first. So this is actually, so let us start. I don't want to disturb this diagram, because we will refer to this diagram for then we'll start Gibbs-Duhem equation. We'll return to solution thermodynamics with Gibbs-Duhem equation. After we finish this, some additional remark about this diagram. So it will be good idea. Figure 4. Written. So this is so I am not I don't want to disturb this figure 4 because I will refer to this. Thank you. So I am removing this part. With this, yes, really we have finished. And today we will discuss, of course, Gibbs-Duhem equation, but only after we finish this additional remark, additional comment. Is okay. Is okay. So we may start with this. This is actually additional remark. Additional remark. Additional remark. Missed out. This was missed out in the last class. In the last class, I'm writing here. In the last class, that is additional remark on example C. The third example is on this one. So last on example C. Example C. So let us start with this. In the last class, in the last class, what will I tell you what? Before actually, this point we will use heavily today. This point. This is y, and this is y dash. So I don't actually. I'm a little bit shifting for. This is y. What happens? This is. Sorry. This is y. This point is y, and this point is y dash. This point, and this is iron stability field. Iron stability field. This is it. Okay. So y and y dash we'll discuss today. This and other things remaining same. last class in the last class, this pen is not, let me check this. So don't do it. Let us not disturb this thing. Okay. In the last class, we decided that we decided in the last class we decided that what is the conclusion, that carbon can reduce, that carbon can carbon this is actually giving trouble here. In carbon can reduce, this was our decision, can reduce APO solid at any temperature above at any temperature above 700 degree centigrade. Remember, it is 700 centigrade. Note that this is centigrade, not Kelvin. Above 700 degree centigrade and 1 atmosphere total pressure and 1 atmosphere total pressure. Total pressure. This was and 1 atmosphere total pressure. 1 atmosphere total pressure. We based our reasoning. What was the reason? Remember that CO2 at Y prime is greater than CO by CO2. Ratio CO by CO2 is greater at Y prime than at Y. This Y prime is actually carbon saturation curve. Y prime is carbon saturation curve. It is APO curve. Since it is greater, it is reducing relative to APO. So we actually consider CO/CO2 ratio, but our final comment was this: the carbon can reduce. This is the problem that I am taking today. To further clarify, we had the conclusion that carbon can reduce APO solid based on the CO by CO2 ratio, CO over CO2 ratio. Not then question is how we are arriving at the conclusion that carbon can reduce. No doubt CO by CO2 ratio in carbon saturated system and CO by CO2 ratio in APO system, the equilibrium value. This is the actual value. This is equilibrium value. So questions still that the clarification is needed. Why sir from CO by CO2 ratio? Well, this is satisfactory that it will reduce. But the question is then, question is why? How do you actually? How you may jump into the conclusion that carbon can reduce? I will explain this. This is the problem today, and we'll ask additional things. Okay, I will take a while. Okay, talking on this, and then we will take up. Okay, so we will return to revert to solution thermodynamics and talk about Gibbs-Duhem equation. So this we last. Our reasoning was based on, we based our reasoning, we based our reasoning. What is the reasoning? Just I am repeating this. The reason that I say based our reasoning on the fact that, what is the fact is this CO by CO2, CO by CO2, this is carbon saturated. That means point Y prime. Carbon saturated line is this A X B. This is X. This we don't need today, but still X. Okay, don't need. Carbon saturated, carbon saturated carbon saturated 800 degree centigrade, 800 degree centigrade at this temperature, 800 degree centigrade, Y and Y prime. See comparison of Y and Y prime. So this is Y prime. Carbon saturated 800 degree centigrade and 1 atmosphere. This value CO by CO2 incidentally I know, or okay, but you can get also from the standard of energy change, etc. If you check this value is 9. It's 9. This is greater than the CO. This is okay. This is greater than this is given by point Y prime, given by point Y prime. That's Y prime. This point, this CO by CO2 here. So this is actually, and then CO by CO2 is greater than what? CO by CO2. CO by CO2. What is this? APO. Okay, APO in equilibrium with APO in this Y point Y. Point Y. Okay, this is CO by APO. These are all equilibrium. This is equilibrium with carbon saturated. This is equilibrium diagram. So this is equilibrium with equilibrium for the CO2 plus C is 2CO, and this is the equilibrium for the APO. APO plus CO is AP plus CO2. APO temperature same, 1 atmosphere. And you write this value also. If you calculate from data, okay, it is actually this value is 1.9. 1.9. Clearly, this is correct from the diagram, from the figure. From the figure, it is correct. This is greater than this CO by percentage CO gives rise to CO by CO2. Okay, so Percentage CO increases means CO by percentage CO increases means CO by CO2 increases. So percentage CO greater means CO by CO2 greater. So CO by CO2 greater at Y prime is than CO by CO2 greater at Y. This I have written here. Okay. This is carbon saturated line. This is APO equilibrium line. Okay. So Y and Y prime. So write this. This is also given by point. Given by point Y. Remember, only one thing I have added today. These values I didn't say. From the diagram I said this is greater, this is less. But today I have given the exact values. Okay. After calculations, you can get the calculation yourself or this. If you calculate, you will get this value is 9, about 9, and this is about 1.9. So this is clearly greater. So this leads to what? Then what we said, with reference to the, now our reaction under study is with reference to the reaction in short. This is reaction with reference to the reaction FeO-CO. Write this FeO solid plus CO gas is Ap solid plus CO2 gas. Call this equation 1. Call this equation 1. Or what I made a mistake is what call this equation 1. This is equation 1. Sorry. This is equation or inequation, whatever you call it. This inequality is given by equation 1, and this is obviously then equation 2. Equation 2. Okay. So this, with reference to this reaction, what we have with reference to this reaction, equation equation 1 satisfies the equation 1 reaction. Equation 1 means this relation equation 1 satisfies, this is last day's discussion, satisfies the relation, satisfies the condition 1 by Q greater than 1 by K. See, the equilibrium constant for this is nothing but CO2 by CO, and 1 by K is CO by CO2. So this is this reaction is under study, and this is subjected to carbon saturated gas or simply carbon. So then, and what is the equilibrium? CO by CO2 in carbon saturated system is this value, which is greater than this 9 against 1.9. So this is 1 by K, so it is 1 by Q. It is actual equilibrium for this reaction. CO2 plus C is 2CO, but acts as an actual for this reaction. This reaction has its own equilibrium constant, and Q coming from here, the other equilibrium actually serving as Q or 1 by Q. So 1 by Q greater than 1 by K. Clearly see, K is what? CO2 by CO. So 1 by K is CO by CO2, which I have written here. So this, or you write this, or what? Q less than K. If Q less than K, or you continue, or delta G is what? Tell me. Delta G0 plus RT ln Q, recall, or delta G, let me write here, give a bracket, delta G is delta G0 plus RT ln Q is what? Is minus RT ln K. This is already started, RT ln Q, which is nothing but RT ln Q by K. Sorry. ln Q by K. Okay. ln Q by K, and Q by K is what? Q less than K is, then Q is less than K is what? Delta G is this. ln Q by K is, from this, is delta G is negative. Delta G is negative. Okay, from this, and hence the reaction is spontaneous. Delta G is negative, that is reaction 2 is spontaneous. That is reaction 2. This reaction understudy. This is understudy. This reaction that is reaction 2 is spontaneous. This much we discussed. And from this we concluded, and of course it was justified, concluded that carbon can reduce FeO. We see CO by CO2 coming from carbon can reduce FeO to Fe from this spontaneous. But we say that carbon can reduce. So this I have to justify today. I will actually clarify this point why we say carbon can reduce this line. See, carbon can reduce FeO. This is actually in terms of CO by CO2 used. So no doubt this CO by CO2 coming from carbon saturation system. So we have to clarify a little bit more so that we directly understand that carbon can reduce. So this part I am actually today's actually discussion, and that is a missed out this point. So let us see. However, how does it follow? However, does it follow from this argument? That is C about CO by CO2. See, Q is CO by CO2. CO by CO2. How does it follow from this argument that carbon can reduce, from the argument that carbon will reduce FeO solid, carbon will reduce FeO solid at, again, that temperature, mention this temperature, pressure 800 degrees centigrade, which is, I am right, I write here in Kelvin, but remember, refer to this figure, it is 800 centigrade. So 800 centigrade and 1 atmosphere total pressure. This is a question. How does it follow? This is the question. Why carbon can reduce it? Okay, this point actually I will discuss this now. Okay, to explain this, what we'll do? Explain this. Consider the equilibrium. Is CO2 plus C is 2CO. Here, consider this equilibrium. CO2 gas plus carbon solid goes to 2CO gas. Call it reaction. Yes, reaction 3 or equation 3. 1 is here, 1 is here, this inequality is 1, 2, this reaction itself, and 3 is the participating reaction or the competing reaction. This one, okay. So this between this, so this is actually third. Okay. So in fact, in a sense, you can say this. We will decide. We are considering these two competing reaction to decide whether carbon can reduce APO or APO can oxidize carbon. This is the question. But our concern is whether carbon can reduce APO because that is the to produce iron. So this is our concern. So iron making. So reduction of APO. So this will to explain this, consider this equilibrium, for which equilibrium this is the 3, and you can write here K3 equilibrium constant, you know very well. K3 is what? Tell me. Sorry. K3 is what? PCO square, as you know, over PCO square over reactant activity of CO2 times activity of carbon solid. Okay. Okay. Activity of carbon solid. Okay. At equilibrium. Always give active at equilibrium. At equilibrium. Okay. EQ means equilibrium. So now you see here PCA square by PCO2 is okay 4. Okay, good. Activity carbon equilibrium. Okay, you just write in write activity of carbon because we understand that solid activity of carbon. Okay, very good, because we have anyway. This is called K3 is call this equation is as 4. Call this 4. Equation 4. Okay. Now it's better actually I remove this top line, this question. Okay. Let us write this. Considering, give a star here, star. Start. Start from here. Considering how you obtain this value, considering activity of carbon, considering the carbon saturated system, concentrate on this. So we actually see how we get the PCO by PCO2 value, CO by CO2 value. Considering the carbon saturated system, which actually this is a carbon saturated system, and we are considering carbon saturated means for which activity of carbon is, which gives activity, which gives activity of carbon is 1. Activity of carbon is 1, which gives activity of carbon is 1, and K2 and K2, K3, and K3 known from delta G0 data. Delta G0 is minus RT ln K, known from delta G0 data available in data book. So this is 1, this is 1, this is obtained from delta G0 data, and okay, what else? And PT is PCO plus PCO2 is 1 atmosphere. Okay. This also have to give a equation name. This is 3, equation 3, equation what? 4. This will be 5. Okay. This is 5. We get PCO and PCO2 each by solving what equation? This is 5 and this is 4. Solving equations 4 and 5. And if you do this, what values they are obtained, and hence we get PCO by PCO2. We can find this. Hence we get PCO by PCO2. It's not easy. See, from this directly, see to get this is the equilibrium. This is the carbon saturated line. This is the equilibrium, carbon saturated line. This is this one, carbon saturated line. CO2 plus C is 2CO equilibrium, that we have considered. Equilibrium constant is this. So how shall we get PCO by PCO2? Well, PCO square by this is P. This is P. Have okay, you should have mentioned this. This is PCO square by PCO2 activity of carbon. So you are interested to find PCO by PCO2 from this. Is it easy? How will you get this? You need to know a few things, namely K3. That is, everyone can find from delta G0, K3. So this is okay. Then what you will get? Activity, if it is activity of carbon should be known. Since we have considered it is a carbon saturated system, means carbon. Since carbon has to reduce APO, this is the question. So carbon saturated system gives you activity of carbon is 1. So known. Okay. So this is known. Still you don't know PCO by PCO2. Because you know what? PCO square by PCO2. Still another relation is required. Another condition is required. What is that? Now total pressure is so pressure specific. These lines are pressure specific. This line is for P is 1 atmosphere. Last day you have seen, and this line is for 0.545 atmosphere. So pressure specific means pressure dependent. So that is also given where? Yeah, here actually you see I have written somewhere. Oh yes, I'm right here. I was discussing here. This is PCO plus PCO2 1 atmosphere. Once you know PCO score by PCO2 and PCO plus PCO2, two equations you can solve out PCO and PCO2 each, and hence the ratio. And accordingly, we have written this PCO by PCO2. How did you get? This way you get. And for APO, very easy, straightforward, because it is no problem. It is pressure independent curve, because 1 mole CO against 1 mole CO2. Pressure has no effect. So also equilibrium constant is PCO2 by PCO. Activity of these two pure substances are 1. So PCO2 by PCO is straightforward. But this is not so straightforward for CO2 plus C is 2CO equilibrium. Pressure dependent. So you might say that activity of carbon saturated, you consider very good. Even though an equilibrium constant is known from delta G0, still PCO score by PCO2. you stuck. You don't know PCO by PCO2. And no one can find y square by x. Y square by x is known. Can you tell me what is y, what is x? Or y by x, even in the ratio form y by x? No. You need another equation. Say like y plus x is this, or y minus x is this, etc., etc. Here it is y plus x means PCO plus PCO2 is given. So we can solve out PCO and PCO2 individually, and hence the ratio. So according to those ratio values, we have seen this. This is a 9, and this is actually for this. This is 9 here, up here, down there, 1.9, 1.9. So this is this. So question is, we get PCO by solving equation. Hence we get PCO by PCO2, which is, we know this, we get PCO by PCO2, right? You write this PCO by PCO2, right? PCO by PCO2, yes, this is actually PCO by PCO2. This is PCO by PCO2. Carbon, so write this PCO by PCO2. Exactly, you can write this. Carbon saturated, we get this PCO, carbon saturated 800 degrees centigrade. Carbon saturated, write this 800 degrees centigrade, 1 atmosphere total, 1 atmosphere. Again, 1 atmosphere, 1 atmosphere, 1 atmosphere, temperature, pressure, etc., etc. And this value is, and this value, if I ask you the numerical value for this value is, already I mentioned. What is this value? Is this means y prime, means what? CO by CO2, PCO by PCO2. Okay, the ratio. See, you see, value is how much? Tell me how much? 9. This value is 9. So you see, this value is 9. Okay, 9 at 800 degrees centigrade. I've written this. This value is 9. Okay. Now I will show you now what I want to do. What I want to do here to show that for carbon, see 3 points at the temperature 800 degrees centigrade means K, fixed K. At activity carbon 1, fixed activity, known activity. And what? Another is the total pressure, PCO plus PCO2 is 1, gives us PCO by PCO2 is what? 9. 9. So conversely, I want to reach to carbon. I have to show, the question is why we jumped into the conclusion that carbon can reduce APO. You are dealing with CO, CO2, etc., etc., but you are saying carbon. Directly show us by carbon can reduce. So what I'll do, I'll show that this value, given this value, see, again see, given 3 things are given. Temperature, this, activity of carbon, will find out that it is 1, coming out as 1, then carbon saturated, means carbon, simply carbon, pure carbon, solid carbon. So this I will find out this time, is not known. I will show that this corresponds to activity of carbon 1 under what? 2 things, temperature 800 degrees centigrade, and what? A total pressure that is used there, 1 atmosphere. So 3 things, remember, 3 things we actually juggle around the 3 things. What? Temperature, this, activity of carbon, another is total pressure. So when we know this, we get PCO by PCO2. Now I am converse way I am trying. I am giving PCO by PCO2 and total pressure and temperature. activity of carbon is unknown, and we will find it out, and obviously it will come out as 1. This actually as 1, because 1 gives this value. So when we substitute PCO by PCO2 with total pressure 1, etc., activity of carbon will turn out as 1, because from 1 we got this value, so from this value we will get back the 1. This is the argument. So now, so let us write down few lines to clarify. Now treating, since I will show that now treat. See, this was accepted last day and today also. This is like CO by CO2. I am going to show that this gentleman is equivalent to activity of carbon 1. Is carbon solid, pure carbon. This value actually how is obtained, I am showed here how it is obtained, and this value is 9. Exactly, I have explained here how it is obtained. So now treating, I want to find out activity of carbon. Now treating as if I don't know, but I know very well that it will be actually the reverse calculation. Okay, the back calculation like this. Now treating activity of carbon as an unknown quantity, unknown quantity, just treating the preceding PCO by PCO2 value. Just I am removing this, and this part I have already introduced the question, so no problem. As unknown quantity, this is right. The preceding PCO by PCO2, the preceding PCO by PCO2 value. What is that value? Write this is 9 here. Is 9 preceding value at 800 degree, again temperature specified 800 degree centigrade. I am writing in bracket, okay, dot, just we are used to writing Kelvin, but this diagram for centigrade, remember, at 800 degree centigrade, and another point very important, and 1 atmosphere total pressure. And 1 atmosphere total pressure. This you have to what here, that is PCO plus PCO2 is 1. PCO plus PCO2 is 1. Okay, will certainly will now treating this the preceding PCO by PC follow, treating this unknown, this preceding PCO by PCO2, this with the help of two things, 800 degree centigrade K, and 1 atmosphere total pressure, another equation. So you see this, this is unknown, activity carbon unknown, and you have PCO plus PCO2. This PCO by PCO2 is known, and PCO plus PCO2 is known. Repeat. So two things. Temperature known means back. How? Very easy. K3 known. Temperature is known. And what is known is here PCO by PCO2 is known. And what else is known? PCO plus PCO2 1 atmosphere total pressure known. Preceding value is known, temperature known, and total pressure known. As a result of which, what will get if these two are known, PCO independently known, PCO2 independently known, then PCO score by PCO2 known, then PCO score by PCO2 is known. So PCO score by PCO2 is known, K is known, activity of carbon will be found out. We have treated this as an unknown quantity. Obviously mathematically we will get activity of carbon is 1. This is the logic. So this is how we'll jump into carbon. Okay, from gas CO2 ratio to carbon, this is the explanation. So it will certainly produce activity of carbon is 1. Following is a converse argument. Following a converse argument. Okay, this is very good. Converse argument. Thus we can conclude. Now the question answer. Thus, so the question was raised and the answer is given. Thus, after we understand this, we are entitled to say that carbon will reduce APO at 800 degrees centigrade and 1 atmosphere total pressure. In fact, any temperature above 700 degrees centigrade, carbon will reduce APO solid at 1 atmosphere pressure. No, otherwise no. If change the pressure, temperature will be changed. Remember last time I said temperature is actually 600 degrees centigrade. I said somewhere I wrote somewhere. Okay, 650. When it is total pressure is 0.45. Okay, very good. So converse, thus we can conclude. That carbon solid, that is activity of carbon is 1. I've written here activity of carbon is 1. Okay, good. Activity of carbon is 1 and carbon solid will reduce APO solid. I'm removing another line. Yes, no problem. Carbon will reduce APO solid at 800 degrees centigrade. At 800 degrees centigrade means 1073 Kelvin. 1073 Kelvin and 1 atmosphere total pressure and 1 atmosphere total pressure. So this is actually our question is answered. So we can conclude that carbon. Why we can conclude? Why say carbon? You are talking of CO by CO2 and suddenly you are commenting, inferring on based on carbon rather than carbon instead of CO by CO2. CO by CO2 coming from activity of carbon 1, but it should be clearly explained why carbon can reduce. This is the question. Teachers will ask students at what temperature carbon can reduce. If you go and find, then the students should ask back what is the total pressure, sir, etc., etc. So and carbon will reduce APO, what temperature. So the students should come with the answer that sir, any minimum temperature is 700 degrees centigrade. Any temperature, answer is any temperature above 700, sir, carbon will reduce APO under 1 atmosphere total pressure. This was the thing. So now there is a corollary. There is still actually this is over, but one auxiliary thing I should want to discuss. Sorry. Okay, so that will be very useful for your carbothermic reduction of iron oxide, APO. Okay. So, so the question is, next question. This is over though. This is over, you may write over, no problem. Initial question, first question answer. This is a missed out point. Today actually we are considering missed out point. This is okay, but next question which comes automatically in student's mind. Next question. How should we, this comes in student's mind. How should we admitting carbon reduces APO? Sir, please give us the reaction then. Obvious question. Obvious. Sir, write the reaction please, sir. If it is carbon, sir, what is the carbon reducing APO at any temperature above 700 degrees centigrade or at 1 atmosphere total pressure of CO2? Very good, of CO2. But give the reaction. That is the question. So that is very important question, because I am telling you, how should we write? How should we write? How should we write the reduction of APO solid by carbon solid pure carbon in the form of a chemical reaction? In the form of a chemical reaction, sir? This is a pertinent question. Student may ask this. Asking. Asking mark. Okay. So this is this. So answer. I am giving you the answer this way. APO solid. You follow me. APO solid plus carbon solid. Okay. I don't think I need this line anymore. This line anymore. This line anymore. Okay. So carbon solid goes to AP solid plus CO gas plus CO2 gas plus CO2 gas. This is, you might wonder, sir, CO, why it is not CO? Why it is not CO2? Why not CO alone? Why not CO2 alone? Then it will be simpler. Or say, under what condition it will be a mixture of CO and CO2? I can give you answer. This will be actually is, since actually we will consider carbon saturated system. So I am giving you the answer. See, above 1000 degrees centigrade. Above 1000 degrees centigrade, you can write it is CO only, CO alone. And below 400 degrees centigrade, below 400 degrees centigrade, it will be CO2 alone. And between 400 and 1000, which 800 degrees centigrade is, it will be CO and CO2 mixture. How many moles of CO? N1. Call it N1, sir. N1 moles. Let it be N2 moles. N1 moles is CO. If it is N1, then you see, make a how many mole carbon? Very easy. Carbon balance. How many carbon you get? From 1 mole CO, how many carbon? 1 mole CO, 1 mole carbon. So N1 mole CO, N1 mole carbon. Again, 1 mole CO2, 1 mole carbon. So N2 mole CO, N2 mole CO2 gives N2 mole carbon. So N1 from here, N2 from there, total carbon is N1 plus N2. Balance, carbon balance, right? So I am writing carbon balance. One trick is carbon balance. N1 plus N2 we get. Then APOs are APO. What you will do? APO is obtained again. See oxygen how much? Right hand side. These two are components where oxygen is present. Not here. Oxygen here. Again see 1 mole CO gives. See 1 mole CO. This is the argument. 1 mole CO. 1 mole C plus 1 mole O. O, not O2, not O2. So oxygen balance. I write this O balance, O balance. And I write here 1 mole, sorry, 1 mole CO. This is 1 mole CO2. What will write? 1 mole C plus 1 mole, 2 mole O, 2 mole of O. 1 mole O2 means 2 mole of 2 molar gram atom of O. 2 mole of O. O, remember O. This is the O. O. Oxygen balance, not O2 balance, right? Not O2 balance. We can make O2 balance also, but oxygen balance may be simpler. You can do also, no problem. I'm not taking up this one. So O or O2, whatever. So O balance. How many O I get from here? 1 mole CO, 1 mole O. So N1 mole of O from this side. 1 mole CO to 2 mole of O. O. So N2 gives 2 N2O. So 2 N2O from this side, N1 mole this side from CO is total N1 plus 2 N2. Oxygen is present in the APO. So 1 mole APO, 1 mole O. So N1 plus 2 N2 mole of O is equivalent to N1 plus 2 N2 mole of APO. Okay. Carbon balance I have written. Oxygen balance is what? Oxygen balance is what? What get? N1 plus 2 N2. This I have written here. O 1 mole APO equivalent to 1 mole O. So, or 1 mole O come from 1 mole APO. So, N1 plus 2 mole of oxygen will come from N1 plus 2 N2 mole of N1 plus 2 N2 mole of O will come from N1 plus 2 N2 mole of APO, same mole of APO. So, this is the entire, no, still iron balance. So, iron is N1 plus, how many moles of iron? N1 plus 2 N2 mole of APO, the left hand side. N1 plus 2 N2. So, this is, remove this side, you don't write unnecessary, easy. This is, give a box there so that it is highlighted, and this is your, so this is your general representation of carbothermic reduction of APO. So can I write this? So this is the general, shall I give a equation name 6, maybe 6, because we have already got 5. We got 5 somewhere. Okay, 5 here, 5 here, 5 here. So 6. So this is the, means equation 6. This is the general representation of the carbothermic reduction of APO. So this is one answer is got, but we have to take a special case. Then further it will be clear, which we will get some value. Maybe I'm trying to give you the answer. Sir, how many moles of carbon will be required to reduce 1 mole of APO? And what is the gas composition on the right hand side, which is actually equilibrium side? So this I'll explain. So the question is, first question is how many moles of carbon required to reduce 1 mole of APO? Give me 1 mole APO. Our interest 1 mole, basis 1 mole APO. How many moles of carbon required? This answer. So this answer with a special case. Okay, special case is actually whether the two things may be possible. One is carbon saturated carbon excess or APO excess. Carbon excess, since 1 mole is given, so we will consider it is actually carbon excess. We'll consider, okay, 1 mole is a finite. APO, otherwise we would say APO excess. So that is not our concern. Our concern is what is the minimum number of moles of carbon required to reduce 1 mole APO. Okay, so but still this minimum is in excess. It means this will correspond to activity of carbon is 1, that is carbon saturated, this line. So this is the, so let us proceed. So this is the next question is still, okay, as a special case, if we consider 1 mole, if we consider 1 mole APO is to be reduced by carbon, is to be reduced by carbon, 1 mole APO is to be reduced by carbon, for which by carbon for which we get what we get 1 mole APO, 1 mole APO, for which we get this is what we get, right? This N1, tell me, 1 mole APO means N1 plus 2N2 is 1. So we will get actually now numbers instead of N1 and N2. So N1 plus 2 we get this, and if we further consider that carbon solid is taken in excess, or there is another term, just excess. In either case, what is the implication? Activity of carbon, excess means carbon solid is physically present, so activity of carbon is 1. So this is the implication. And just excess also, carbon just disappeared, just used up. So under activity of carbon is 1. These are the two meaning. In either case, activity of carbon is 1. So just excess, why I have written here? To avoid, why just excess? Just excess to avoid, to avoid wastage of carbon. Wastage of carbon is very important to us. We do not want to waste coke or carbon, because coke rate is a very important issue. So do we want to avoid? So it is just excess, means carbon will be utilized but under saturation, just excess. This is the meaning of this, but okay, if I have time, okay, this is the one. So that next is so we consider that carbon is taken in excess or just excess to avoid this. So that the consideration, so that the consideration activity of carbon is 1. Excess, you consider excess carbon is physically present, activity of carbon is 1. Just excess is also similar, only there is no, okay, this is still under, this appear just under carbon saturation. Okay. So so that the consideration of activity is justified. You have to either consider carbon saturated system or the opposite is FeO saturated system. Okay, but here we actually, to find this minimum amount of carbon required to reduce 1 mole FeO, it is actually we are considering carbon saturated system, means we are referring to Y prime point. Let us follow this. Let us follow. You will automatically get this. So the consideration of activity carbon is just, remember, activity of carbon is what here on this carbon saturated line 1, and you have actually different activity below or above. Okay, so what is this is valid, is justified, and at a temperature, and give the temperature, and at a temperature of 800 degrees centigrade that we are using 1073 Kelvin, and 1 atmosphere total pressure, what is that? PCO plus PCO2, PCO plus PCO2, 1 atmosphere total pressure, for which temperature of this, and 1 total pressure, for which I am writing here, I am writing 9. You know, PCO by PCO2, we have seen this value is 9 under carbon saturation. I removed it. I've shown number of times is 9. Yes. This is 9 actually for carbon saturation. So 9, if carbon saturation, then PCO by PCO2 is how much? As I've removed this, are also still showing here. This is 9. So this point PCO by Y prime, PCO by this is a percentage here, but PCO by PCO2 is 9. Okay, this I said. Okay, so very good. 9 is PCO by PCO2. Achha, why? PCO by PCO2 for this. This is PCO2 equilibrium. Remember, you should apply this carbon saturation, because system is excess carbon or just excess. So carbon activity 1 under this condition, obviously this you have this 9 is here. These gases are under carbon saturation. So what is the relation? Is this 9 is PCO by PCO2 equilibrium is NCO by NCO2 equilibrium. PCO means ratio means NCO equilibrium is, what is this? NCO is how much? NCO is how much? N1 is N1 by, so 9 is N1 by N2. Okay, and what else we have? What equation? We want to solve N1 and N2 and write this in figures, numbers. So one equation I have got, because PCO by PCO2 under carbon saturation is already found to be 9, and you have written number. Okay, last day also it was said that PCO by PCO2 is here 9. Okay, okay, very good. I didn't give this number 9 last day, but today I have given it. It is 9, and it is perhaps 2.6, etc. This I said. Didn't I say this? How much it is? This is about 1. I'm sorry. This is 1.9 means about 2. This is 2, this is 9. 9 greater than 2, I showed there. So what else? To get N1 and N2, one equation, still another equation required. 1 mole of FeO. So, and what is this? N1 plus 2N2 is 1 mole FeO is 1. ঠিক আছে? N1 plus N2 is N plus 1. Okay. So NCO by NCO2 is 1, N1 plus 2N2 is 1. Okay. So we can solve N1, solve. Shall I give a star mark, double star maybe, double star. Remove this. Remove this. This is all discussed. Remove this. Okay. Thank you. Double star. Solving N1 and N2, we get what? We get N1 is how much? Tell me. N1 by N2 is 9. So N1 is 9N2 and 9N2 plus 2N2, 11N2. So N2 is 1 by 11 mole. Repeat quickly. N1 by N2 is 9. So N1 is 9N2. 9N2 and here plus 2, N1 is 9N2 plus 2N2 is 1. So N2 is 1 by 11 mole. And N1 is how much? N1 is nothing but 9N2, 9 times 9 by 11 mole. So the reaction, so the overall expression is 9. Substituting the values of N1 and N2, what? N1 and N2 in equation, what equation? Here. It is in terms of N1 and N2. Now it will be in terms of numbers. Okay. In equation what? 6. In equation 6, what you get? What you get? Equation? Sorry. Equation, sorry. In equation 6. In equation 6. 6 means this. What you get? Right. N1 9 by N1 plus 2 into 2 into is how much? N1 plus 2 into is obviously 1. So it's in here. So 1 FeO as it should be. 1 mole FeO was taking. So substitute this FeO solid. Sorry. FeO solid. 1 mole N1 plus 2 into is 1 plus N1 plus N2 is how much? N1 plus N2 9 plus 1 is 10 by 11 plus 10 by 11. What I have written here? Carbon. I am writing mole. 1 mole. I am writing 1 mole. Op is not needed. Then mole. What? Carbon. Carbon solid. 10 mole carbon solid. I am sorry. 10 by 10 over 11. 10 over 11 mole of carbon solid. Sorry. Plus 10 over 11 carbon is again N1 plus 2 N2 means 1 mole Fe as it should be. So I write here 1 mole Fe. 1 mole Fe solid plus what shall I write here? Tell me. N1 CO. N1 is what? 9/11 mole CO plus 1/11 mole CO2. This is actually the carbon that is actually we have considered. This is actually which is just excess. This is a minimum. So this is a minimum number, means just excess. Don't use okay, more than excess. No, that can be still activity. This is, so I'll show that if you take more than this. Let me write few lines. Let me write a few lines here. Then everything will be clear. So this is, can I give a, this is also nice observation. What in a carbon saturated system? But a few more comments will be helpful. Remember, this gas composition is referring to what? This point. What is the CO by CO2? See, 9/11 divided by 1/11 is 9. As you remember, this value was 9. I have repeatedly said this point is 9. Okay, so very good. Today, I've said this thing today only. Okay, not yes last day. But anyway, I've said number of times that this is 9, and also based on this I calculated somewhere. Which is 9 here also. It is showing there. 10 here. Don't worry. Over. So few comments will be helpful here at this stage. Shall I give okay. Okay, very good. Now note what you will note. The equilibrium state of reaction of reaction, what is called 7 is what? This actually has been given a name 7, I guess. Yes, call it 7. Important. Call it 7. Achha, the equilibrium state of reaction 7 is given by what is happening this way is given by point. Which point? This equilibrium state of this reaction, equilibrium state given by point y prime. This CO2 gas and carbon activity is 1 saturated at this point given by this. Okay, given by point y prime. So graphically you can show the equilibrium state, the y prime. Okay, that is right. That is right. CO by CO2 is 9. You can check here. CO by CO2 9/11 divided by 1/11 is 9. CO is point y. Y that is actually is on the y prime on the carbon saturated curve. On the carbon saturated curve. Have I mentioned here? Okay. Remember, 1 atmosphere total pressure means this curve is pertinent. This curve, not this. 1 atmosphere total pressure. So you understood this. I have already explained on the carbon saturation curve. Carbon saturation curve. Carbon saturation Carbon saturation curve means this one. What is the okay? What is this carbon saturation? What is the name? A X last day. A X B. A X B. Carb A X B. Is clear there? Okay, last day I explained this in the carbon saturation curve. The right hand side of reaction 7, note this. Don't need this anymore. Okay? The right hand side of reaction 7 reaction 7 gives the right hand side. This here is the equilibrium state. Charge allowed to react, stop here. Only thing which you don't see here but implied is this, or you may write a carbon which has just disappeared under saturation. So this and carbon activity 1, or if it is excess carbon, then some carbon also. So these plus excess carbon after the reaction. This is the equilibrium state. This is the initial state. It charged to arrive there. The reaction is here at equilibrium, and this is the equilibrium state, as I said. So right hand side of reaction 7 gives the equilibrium state. So let us try. Let us change the pen. Gives the oh, it doesn't. Gives the equilibrium state of the reaction right hand side only, right hand side, with left hand side what here? Carbon saturation or excess carbon physically present, plus this plus excess carbon or just disappear under carbon saturation. So that refers to the minimum carbon that I am coming to take up soon. Okay, but just 1 or 2 minutes. Okay, state of reaction under activity of carbon of the reaction under activity of carbon is what? This is called carbon saturation. Activity of carbon is one called saturation. That is when under what condition? With the excess carbon, then no problem. Then no problem. Carbon is seen in the reactor is left behind. Excess carbon and carbon activity should be 1. Excess carbon, or as I have said, or just excess. This is meaningful. Just excess refers to the minimum. You don't need any more, and still carbon activity is 1. So it just disappears under unit activity. No problem. I have discussed this before, I remember. Or just excess carbon Hence, it may be inferred that that the minimum carbon minimum carbon to reduce 1 mole. We took 1 mole, 1 mole APO solid as a minimum carbon. This minimum carbon implies that just excess, not beyond, not more than excess, just excess. This is not excess, just excess. Means it will be sufficient to maintain activity of carbon, and also no carbon will remain unutilized. This is the so this reflects what? This is the situation of minimum carbon. When minimum carbon, the situation of situation of of just excess, underline just excess, situation of just excess carbon. That refers to minimum, and which are interested minimum. But the minimum carbon, we don't want to waste carbon. So carbon will disappear, will be utilized, will not be in the system, but maintaining unit activity, that's possible. Okay, so so this is just excess carbon. Okay, very good, just excess carbon to reduce 1 mole APO solid 1 mole APO solid reduce 1 mole APO solid is how much? What is the carbon requirement? Minimum carbon. That the minimum carbon to reduce 1 APO is what? What is the minimum carbon? I'm sorry, 10 by 11. This is the answer. 10. This is the case where we have considered that this is fully converted into CO2 and producing iron, fully utilized. So this is the minimum. So, and because we have considered just excess carbon. Why? Because this is the minimum carbon we are interested. Carbon, okay, is 10 by the minimum amount of carbon will be there will be carbon wastage is 10 by 11 from here. What is this value? 0.91 is 0.91 mole of carbon. So you have the whole story. Temperature chosen 800 degree. So at 800 degree, to reduce 1 mole APO, you need 10 by 11 mole of carbon minimum. That is 0.9 mole of carbon, and the 1 mole of iron will be produced, and the gas composition will be 9 by 1 mole of CO and 9 by and 1 by 1, 9 by 11 mole of CO and 1 by 11 mole of CO2. So this is actually, so CO is to CO2. Okay, CO by CO2 is 9 by 1, is 9. Okay, this is the equilibrium gas composition, which is given by the point Y prime, as I have said here. Okay, I have already explained this. So this is your answer. How much carbon is required? 1 mole of APO. First answer you get what temperature at 1 atmospheric pressure carbon can reduce APO solid? Your answer is any temperature greater than 700 degrees centigrade. And you chose accordingly 800 degrees centigrade. Then next question is, what is the stoichiometry reaction? So under this condition, considering this, actually this will be carbon saturated, not APO saturated. APO, if you ask me what is APO saturated line, you know. If you ask me this point, you know. APO solid is present. So this is APO activity is 1 here, solid. Here, and above this iron is pure, stable. APO is not. So APO activity is less than 1. So this point is APO activity is not 1, less than 1, unsaturated. That is no problem because APO has been removed, has been reduced, and that's why it is not here. Final equilibrium state, what you have? This. And if carbon excess, then excess amount of carbon. So that I'll explain now. So 0.91 mole of carbon. Now can I remove this? This is actually already important, though general representation, but we have covered this and no point retaining this. Okay, 0.91 mole of carbon. So this is okay. Under this situation, this situation is just excess carbon. Under this situation, what will happen? You see, all carbon will be used up. Producing means it will utilize to reduce APO, producing iron and 1 mole iron and that CO and CO2, that those moles of CO and CO2. So under this situation, under this situation, 0.91 mole carbon reacts, will be removed, will all be removed by reaction with 1 mole APO, with 1 mole APO under carbon saturation. Normally we think saturation means some excess is there, then it is very cheap. Everyone can understand. But when it is just disappeared under carbon saturation, this you can very easily test. If you add 1 grain of carbon, when carbon is fully removed, there no more reaction. Means it is already, this grain of carbon has activity pure, being pure, activity 1. So in the system there is activity of 1 carbon. Carbon with 1 activity, unit activity. Means although absent, it actually is present in unit activity. I can give an example. I gave this example, sugar. So you are actually making a sugar solution, syrup. Take water, add sugar, small, few pinches. It dissolves. There is a solubility limit, you know. Suppose 0.2 gram is a soluble. 10 gram for 10 cc water, 0.2 gram will be saturation. So let us add this. So first you add 0.2, so 0.01, 0.02, 0.1 gram dissolved, unsaturated. 0.2 is the saturation. 0.15 dissolved, it is an unsaturated solution. 0.4 0.2, I'm sorry, 0.15, 0.17, still unsaturated, 0.19, still unsaturation. When you add 0.2, exactly 0.2, it is saturation, but you cannot identify. It is saturation because you don't see any sugar settling at the bottom. No, you don't see. But the moment it is 0.2001 gram of sugar just exceeded, that 0.001 gram of sugar will settle at the bottom, and you say it is a carbon saturated, I am very sorry, sugar saturated water. Means this syrup is saturated with sugar because solid sugar is settling. Water cannot take up anymore. That previous point, when it was just 0.2, you don't see. It is like here, you don't see carbon, but it is saturation. Just saturation, just remove under saturation, and that also refers to the minimum carbon. So that we are interested in minimum carbon. So under reaction with 1 mole under carbon saturation. Where I am under carbon saturation, E under carbon saturation. That is right here. That is complete this under activity of carbon is 1. Carbon saturation means activity of carbon is 1. Okay. Next. Now if now you be clear. If so 0.91 mole of carbon, you removed 1 mole, reduced 1 mole APO, and your job is done. 1 mole iron is produced. If you added more than that, your requirement is minimum is 0.91, but you add more than that. But if a greater amount of carbon, say 1 mole of carbon is charged, excess, you have charged more than minimum, is charged, then what will happen? 1 minus 0.91 is requirement, because the required amount is 0.09 mole of carbon will remain unutilized in the system at equilibrium. And here, so you see, so you added more than 0.91, say 1 gram, so 1 mole, 0.91 mole is the requirement, 1 mole, so 0.09 mole will be sitting in the system, carbon, unutilized. Along with this is also carbon. This is obviously, clearly it is activity carbon 1 because carbon physically present. The tricky part is that carbon when just gone. This is the trickiest part or tricky part. There you have to consider this is gone under carbon saturation. And remember, in either case, the moment is carbon activity, unit activity, and this temperature and total pressure is, I mentioned here, I still see total pressure, temperature, pressure, and carbon saturation. Then you refer to this curve. Depending upon the temperature. So any temperature, giving the pressure and carbon saturation, this will be your curve and the point Y. So here, when it is excess, still equilibrium is this point because it is dictated by the CO2. If iron is some carbon is excess sitting, no problem. It is still this composition is saturated with respect to carbon. So this is the whole story. I think I have discussed this point. So next is, I'll start this as what is things. I actually took much time to discuss this, but this was very important. And so see how difficult is the concept of equilibrium. This I said. Four issues of thermodynamics. One I said first is the D, use of D, differential D. Second I said reversible process. Third I said what? Use of constraint like DGPT, DUBT, DABT, DUSB, etc. etc. Okay, DSUV, etc. etc. DHSP, etc. etc. So many constant use of constants. Second, third, use of constant is the third. Fourth is concept of equilibrium. See how difficult it is actually. You have to that when it is a multiple reaction, and then you have to use it will be more complicated, more involved. Okay, so that's why I asked you to be alert about these four issues. Thank you very much. So next is what I start with this quickly. I'm removing this. I'm removing this. Four issues all removed. All removed. Clean. Clean. All over. So now we actually left off in the middle after we discuss excess functions and so on, and temperature dependence of temperature dependence of activity coefficient for positive deviation system and negative deviation system. So this I discussed. Then then further we actually consider that is partial molar free energy from integral molar free energy, tangential intercept. Then perhaps we actually stop whatever it is, but we remember Gibbs-Duhem equation. So solution thermodynamics. Let me check whether this I can have a better solution thermodynamics. Resumed. We stopped in the middle and we discussed these four issues. Then let us revert to solution thermodynamics. What is the topic here? Gibbs-Duhem equation. Gibbs-Duhem equation. And its integration will be followed after we Gibbs-Duhem derive Gibbs-Duhem. We will derive Gibbs-Duhem equation. Okay. So what is this? Start. For a, it is better I give a line this, for a multi-component system, or solution say 1, 2, 3, 3 component system, 1, 2, 3 solution, that is what type of system is solution system or chemical reaction system is variable mass, that is system with variable mass. You may write this, that is system with variable mass and variable composition. I will explain this. I have already explained, but
1 hour 45 minutes.
Okay, 10 minutes maybe. Okay. This I write this G prime starting line. This remember, this is a starting line. Starting line you have to write correctly. Then subsequent lines, the following lines, the lines that will follow is easy. First line is most difficult. In thermodynamics to write like here, starting line. Is what starting line is what? G prime, the free energy of the system. Solution is a single phase. Is a function of, on many a time I have written pressure, temperature. Since three components are there, N1, N2, N3. This line. See, you just cannot memorize this. Also, just it is actually a matter of habit. We write this ritual. No, you understand this. Remember, always remember these are what? Independent variable. Independent, right hand side independent variables, while the left hand side is dependent variable. I will take an example to show why we are entitled to write this. I will take an example. I am taking a system, solution system. Solution system, this system will, variable mass with variable composition will be shown. And so two things I will show. Why it is variable mass and variable composition, and why it is like this. So this is solution. So here it is a what type of solution? To be practical, iron, manganese, silicon system. Very common to iron making and steel making. Iron, manganese, silicon system solution. So solution, this is a solution. And what is single phase? As you know, single phase. And what we have taken in this, NFE moles iron, NMN NMN moles of manganese, and N silicon N silicon mole of silicon. We have taken in this system, iron, manganese, silicon. This is thermostated at a given temperature. Temperature T, and there is a pressure under certain pressure. P. So P. Okay. So this. Very good. Suppose NFE is 6 mole. NMN is 4 moles, 3 moles and 1 mole. And in silicon is 1 mole. So 6 mole, 3. Now seeing this, can I write this? First of all, what is the what is the composition? X iron, mole fraction. Composition is mole fraction. Composition is given by mole fraction. So XAP is, for example, is what is XAP? You know very well. 6 mole by 6 plus 3 plus 1 is 0.6 mole fraction. This is a composition. Similarly, manganese, similarly silicon. Okay. But what I try to mean here, first of all, you follow whether I am entitled to write this. See, pressure I fixed arbitrarily, independently. So independent variable. Why? It can be 1 atmosphere, can be 2 atmosphere, can be 10 atmosphere, can be 0.1 atmosphere freely. Temperature can be, since it is steel making system or iron making system, say it is 1600 degrees centigrade, 1873 Kelvin, or maybe little less, 1500 degrees centigrade, 1550 degrees centigrade, arbitrarily. As long as this is a single phase and possible, no problem. Or say 1650 degrees centigrade, no problem. So variation. So independent. So independent. N1 moles. I have written 6 moles. I could have written 7 moles. So 3. N1 is iron. This is the iron. Say this is the iron. 6. It can be 7. It can be 8. N2. 3 mole. Can be 2 mole. Can be 1 mole. Can be 5 mole. Similarly, silicon can be 1 mole. 1 mole I consider it can be 2 moles or 3 moles, etc. So these are 3. So hence they are independent. You independently charge. Fixed temperature independently. So they are this. So this line is correct. And G prime is the function of this. Free energy is a function of, free energy function of this. Pressure, temperature, VDP. Free energy is a function of pressure as VDP. Temperature minus SDT. And here also you will see actually this will be function of G1 bar, etc. This will see partial molar free energy 1, 2, 3, etc. This I will show you. So now I will show you what. Now here also this is one point I have clarified. Another point, this one, system with variable mass. So it is variable mass. Mass is variable mass. Say 6, 3, 1. I am taking it. So instead of, if 8 gram mole, follow this. See, if 8 mole iron is used, was taken, then what is the XAP? XAP is what now? See, 8 by, other things I have not changed. 8 by 8 plus 3 plus 1 is 8 by 12 is 2/3 is 0.67. So X composition has changed. So yes, composition. So variable mass variable. Is it variable? Mass clearly variable. The moment mass are variable, so for example you are changing freely, composition is also variable. Composition also changing. Variable composition. This is the meaning of this fixed variable mass with variable composition. Another system I can show you here about this. Another system. These are simpler gas phase system. Another system similarly, I am showing you. You have taken CO2 gas, O2 gas system. Again similarly, this is the pressure arbitrarily chosen. There is a temperature independently chosen, freely chosen, and moles of CO, CO2, O2, any amount. So this is also, so what is this? This is actually the single phase. This is also single phase gas. All gases form single phase. Okay, one phase mix. Okay, by all proportions. So on single phase. Okay, this. So what should I write? Hence here you write here. So hence you write here previously. Hence it is a variable mass. Previous case. Variable mass with variable composition system. This one, variable mass, as I have said. Solution system. This is also solution. This is the gas phase solution. So similarly you can say, hence is variable mass. It is better to write here as well as variable composition. See, I have showed here change, mass change, variably, composition changed. Okay, or 5 minutes. This is okay. Single 5 minutes. Single phase gas. Okay, this also similarly, you take any moles freely and composition, mole fraction change. So these two systems, these are both. This is also a variable mass as well as and variable composition system. Now today, before I'll give you an example. You may ask, sir, is it possible to have any? Okay, this figure 1, figure 2. Is it anyhow possible variable mass but not variable composition? Mass variable I can take. The composition does not change. Yes, it is possible. So that I'll show you. So I'll take you. This is figure 2. Figure 3 here. This also I discussed before, but you may have forgotten or you didn't. This is again pressure. This is again temperature. But note this, what I am doing. I am taking a reaction system, Nm moles of M, NO2. Actually, it is better I write here. Nm mole M. Also another thing, NO2 mole MO2. Another solid metal MO2. I have taken NMO2 mole. This is Nm mole of M, and also the gas remaining is gas NO2 mole of O2 gas. This thing I have taken. Now what happens here? So arbitrarily again I took say 4 moles, 5 moles. Take NMO2 6 moles I can take. I can take oxygen 3 moles, 4 moles. So all can be independently. So again this, and also for chemical reaction delta G is a negative or 0, etc. Starting line was this. This is also starting line of chemical reaction. So this, but there is a great difference here. This is in fact a chemical reaction, but great difference is here. What is this? So into NO2 mole of gas. But is it what? Is it a? This is a variable mass. This is variable mass. This is a variable mass, and what should we write here? This is a variable mass without variable composition. Without variable composition. Why? So here the moment you moles changing variable mass 6 to 8, variable composition 0.6 to 0.67. Here similarly I have not shown same. Here you change Nm moles. So it is 3 moles, we added 4 moles. Is the composition, does the composition change of the system? Because they are separate phase. This is a single phase, 3 phase, right? It is a 3 phase system. 3 phase system. What are the 3 phase? Independent. 2 solid, 1 gas. They are not miscible. They are separate. They are pure. Each is pure. So you change the pure Nm moles, means say consider Nm is say 3 moles. You add 4 moles, so what? It remains pure. The composition, it was pure means mole fraction 1. for M, pure. 4 moles still pure, same composition for M. And MO2 likewise 2 moles to U2, then 3 moles U2, then still pure, and composition means mole fraction is 1 for MO2. This phase, in this phase MO2 alone is present, so pure MO2, so mole fraction is 1. This is 1, this is 1, and gas alone is present. So 3 moles or 4 moles of oxygen, so in the gas phase, mole fraction of oxygen in the gas phase is 1. So without, you can increase this, change the mass, composition does not change. Variable mass without variable composition, very important. But this is a chemical reaction system. This is also a chemical reaction system. CO plus half O2 is CO2. Okay, this I wrote somewhere. Okay, so just consider. So this is figure 3. Figure 3. So I write here. I remove this part. Figure 1, figure 2, figure 3. Summarize. I summarize here quickly. I summarize here. Then it will help. Summary. This will be helpful. Figure 1 is what you can write is a solution system. Figure 1, figure 2, figure 3 is a solution system. Is a solution system, and what is the solution? You write, okay, Fe, Mn, Si means silicon. Okay, how do you write here? G prime. Write this. This is important. G prime is, as you have understood, function of pressure, temperature, Nfe, Nmn, Nsi. You have already understood this. Okay, very good. Next is figure 2. Achha, figure 2, what type of system you will add here? What type of system? Tell me already. System with variable mass and variable composition. I am writing in short. System with variable mass and variable composition. Composition, as I have already demonstrated. Figure 2, little below. Figure 2. Figure 2 is a what type of system? It is not a solution system. It is a reaction system. It is a chemical reaction system. It is a chemical reaction system. What is the reaction? You can write underneath CO plus half O2, CO gas plus half O2 gas is CO2 gas. Is CO2 gas. Happy? Chemical reaction system. How will you write here? G prime is a no problem, same function of pressure, temperature, so all freely changed. NCO, NCO2, NO2. Only this is a solution system. This is a chemical reaction system, and this is also last figure 3. Figure 3. What shall I write? I will remove this part. Figure 3. Achha, what you write here? This is also. See, I am not writing. This is also system with variable mass and variable composition. So that I get space for figure 3 and time also. Figure 3, you see. Figure 3 I will write here clearly. This is ditto. Remember, this is ditto. Figure 2. This is also I wrote here. This is also. So I have written here same. Figure 3 last is a, again it is a chemical reaction system. Is a chemical reaction system. What is the reaction? M solid plus O2 gas goes to MO2 solid. This I have used number of times, okay, previously. So here how will you write? G prime is, right, tell me, function of press. Similarly, tell me, sorry. Pressure, temperature, tell me, Nm, NO2, NMO2. This is what type of system? Very important. Underline, this is very important. This is a variable mass system with variable mass. So the variable mass in three cases, variable mass, but here no variable composition. Composition is not changing, but here changing. So variable mass without, very interesting, without variable composition. Again, so interesting is this. How to write this? I have written here, NMNO2. What else I should write there? This is a figure 3 is a chemical reaction. This is. So very good. So these two same system with variable mass and variable composition. These two. Figure 3 is variable mass, but without variable composition. So they remain same composition in mole fraction 1, pure. So last thing is this. However, I write here. However, remember next day I will start from this point, this I have written. I'll start from here and arrive at Gibbs-Duhem equation. So today I don't have time. Just a last point I say. However, if we consider, this is another interesting thing. If we consider 1 mole of ideal gas, 1 mole of ideal gas, 1 mole of ideal gas as system, it will be an example of, what? Of variable mass. 1 mole given. So fixed mass. And obviously 1 mole, this is only one gas, fixed composition. Example of fixed mass and fixed composition system. And in this case, tell me, what shall I write? G prime. You can write G prime, but I am not giving prime here because it's 1 mole, so it is intensive. So G, no problem. What you will write? This case, in this manner. And what is this? In this manner. What you will write? Function of pressure, temperature. Nothing else. Okay, this is fixed mass. So broadly, this is special. This you have read number of times. 1 mole of an ideal gas is a system. You have two independent. You can take it at any temperature, any pressure. So this is only this. While these are this. Thank you very much. With this, we have completed today's lesson. Okay. Thank you for your cooperation and for your interest. See you next class, and we will actually work with Gibbs-Duhem equation starting from this line. Okay. Starting from this line. Thank you. See you.